All right, I'm going to get started a little bit early, see if we can fit a little more in today. So last time we, in simulating a quantum computer, we tried to take a new approach that was meant to involve less matrix multiplication, which we had seen was bottlenecking the performance of the app. So idea was that we had these matrices that were 2 to the number of qubits by 2 to the number of qubits, and that's all fine and well when the number of qubits is 4 and they look like this, but when the number of qubits got a lot larger, multiplying these matrices together did not go well. And so we sort of started diving into the internals of quantum circuit, looked at doing things qubit by qubit, with the idea being that we would just do sort of two-dimensional matrix multiplication at most. Sort of ran into a problem, though. When we got deeper into it, it became clear that we were going to run into the same thing, because each time you, say you want to apply a 2-qubit gate to a 10-qubit system, 2-qubit gate just on the last 2, you still need to every basis factor, all 2 to the 10 basis factors still have those 2 qubits in them, so you still have to apply your 2-qubit gate in some way to all of those basis factors, which is just doing matrix multiplication. It just works out to be matrix multiplication again. So that didn't work. So we reverted a bunch of that. I mean, we got a few things cleaned up, but reverted that. It happens sometimes. You usually learn more about your code. I kind of think of this, if you play chess, there's this thing where you calculate some long line, you realize it doesn't work. It feels like you haven't accomplished anything, but in reality, you reuse parts of that calculation or ideas from that calculation in other lines. And in the same way, we're going to be able to use the thinking that we did in the process of trying to work out to do in order to actually solve this problem, and maybe improve things down the line. So we did a little bit of thinking about sparse matrix multiplication, because really these are quite sparse matrices. They get sparser the bigger that they are. There are a lot of zeros in these matrices. And we looked at some of what's available in the Rust ecosystem. There is an N-algebra sparse crate. Dug around in that a little bit, but it became clear, or not clear. I think it's probably usable. Maybe it's what we should use, but we could also just roll our own. And I usually shy away from rolling my own in situations like this, because it's one more place where I can introduce bugs. It's potentially a bunch more work. It's unbounded, whereas usually you figure out some dependency, it's being maintained, you figure out the dependency, how it works, and you end up spending less time both understanding it, building it, and maintaining it. But in this case, I think, our goal is not to write production-ready software here. Our goal is to understand quantum computing better and learn things. And I think, I'm not sure sparse matrix multiplication will teach us much about quantum circuits necessarily, but it certainly will teach us something about algorithms and matrix multiplication. It's not something that I've done before, so it's going to be new for me as well. So I think this session, basically what I want to do is replace the matrix. We have our own wrapper type, and this is one of the nice things about creating a wrapper type. We have our own wrapper around D-matrix complex. So this is an N-algebra library provided dynamic matrix of complex numbers. And I think we just want to swap out the internals of this for a better representation of a matrix, and a better representation of a sparse matrix, and matrix multiplication that is way faster. So let's think about how we would do that. And I did a little bit of poking around. I didn't look too much into the algorithms, but I understand the basic idea. So the basic idea is, let's look at one of these matrices. So we're either doing, let's just take these first two, right? In our case, we either are left multiplying a matrix by a vector. So in this case, the vector is not where it should be for matrix multiplication. The vector would be on the right. But that's one operation that we need to do quickly. And I think that one wasn't too slow. But the bad one is when we multiply multiple of these matrices together. That one was really, really slow. And so what's the idea behind a sparse matrix representation and a sparse matrix multiplication? Well, the idea is basically that there are a whole lot of zeros in a sparse matrix. That's how it's defined. And that means that you can skip a whole lot of computations. And so I think the kind of naive implementation here is going to be to store the entries as a hash map of a hash map of the value. So let's say it's either going to be row column value or column row value. And then to instantiate the resulting matrix by just filling it up with zeros. Or maybe we don't even need to do that because we can just instantiate a new hash map. And then you never have to do any calculations with your with values that start with zero. So say we take, these two matrices. We represent them as, 0, 0 maps to this value, 0, 1 maps to this value. We don't store this. We don't store this, and so on. 1, 0 maps to this value, 1, 0 maps to this value. We don't store this, and so on. And then same thing with this matrix here. Now, to construct a new sparse matrix, namely this one, we're sum producting this row with this column. This row has almost no entries in it. So really what we'll do is just say this entry contributes by sum producting with this row to the 0, 0 element. And this entry contributes by sum producting with this row. But none of the other ones need be calculated until we get there, and then we can continue to mutate the value in place. So we should only essentially we're only going to do one sum product for each time that we see an element in the left-hand matrix. And that's what's going to make things a lot faster, because the regular way of doing matrix multiplication is you have to look at each of the coordinates of the output matrix and multiply a whole row by a whole column. Instead, we're going to look at each of the coordinates, but we're just going to multiply. we're just going to multiply we're only going to bother looking at an element of the output if there's an element of one of the inputs. And because there's so few elements in one of the inputs, it's going to end up being something like, this is whatever, 4 times 8, so 32 squares here. So maybe 32 different calculations rather than, 16 squared different calculations. So I think that's going to be the idea. And then we'll just go from there. If it's not fast enough, we will try to optimize. And hopefully we learn something. Okay, cool. So, let us create a new type, I think, that knows how to get itself from a D matrix. So let's see if we just have type sparse matrix is a hash map of U size to U size complex. This is the row, this is the column. Do we want to do it row based or do we want to use it column based? Hey, handle file. How's it going? Do I use Copilot? Yeah. I have been using it for the last few months. I was pretty skeptical about it at first, but somebody I trust recommended it to me, and I started using it and found, especially with Rust, I haven't used it with any other languages, a little bit of Elm, but especially with Rust, where things are so constrained by the type system, I found it's like quite useful for getting, especially for just like populating boilerplate and populating, like sort of things I don't bother remembering in APIs I don't use frequently. It populates them pretty quickly, which is really nice. The downside to it is that sometimes it writes bugs. And so you have to make sure that you don't just like blindly trust Copilot. But it's been generally, I think, beneficial to me. I'm not completely sold on it yet, but I think it's been good overall. I do indeed sometimes also write bugs, that's for sure. But there is at least for me, it can be easy sometimes to trust Copilot too much, whereas I don't trust myself. So it's just kind of making sure that I actually check that. Like Copilot filled this in where it's like usize and then a tuple. Why shouldn't this be a hash map of usize to a hash map from a usize to complex? I saw some things when I was reading about sparse matrices that suggest to me that this is the right way to do it, but I don't totally understand why yet, and if I don't kind of interrogate that, then I might end up doing something I don't want to do just because Copilot suggested it. Okay, so let's impl sparse bit. Let's impl from for D matrix complex. Let's see here. I want to be able to go from D matrix complex for sparse matrix. And here Copilot has helpfully tried to write a function for me. So to your point, let's check that it's actually good. So we're iterating through the rows, we're getting the index of it, and then the row itself. We're doing the same thing with the columns, and then if the coefficient isn't 0, we're inserting it, which looks correct. Is 0 a thing? Yeah, so here's an example. I didn't know is 0 is a thing on complex numbers. I would have written this as equals 0. So this is a nice little improvement from Copilot. And yeah, okay. I couldn't remember if I was allowed to do this. I guess I'm not. So let's go ahead and create a struct. One of the nice things about Rust is that these sorts of structs are zero cost abstractions. And let's say, do I need to store the size? I guess I do need to store the size. But now Copilot is trying to force me into a different thing that I don't want. Your best joke about Rust. Rust has a compile time garbage collection. It collects all of your garbage code into binary. Yeah. I mean, it's complicated. And why don't we like this? Oh, because I need to actually instantiate the sparse matrix. Let's go ahead and give it a new function also. And it's not what I want. I want to actually provide data. U size to a U size and a complex F32. And then this can become sparse matrix new of that. Okay, now there's also a question. So this is indexing based on rows. So I'm going to have an entry in the hash map every time there is a row that has elements. I'm just thinking about whether it makes sense to do it with rows or with columns. Certainly this is a little more ergonomic. In my case, I'm thinking about whether vector... What's the problem? Oh. I'm thinking about whether vector multiplication by a vector is going to be faster with one or the other. Seems like if I know that there's nothing in the row, then I can skip an entire calculation, an entire left multiplication by a vector, because left multiplication by a vector is just like comparing my whole row to the whole vector. So intuitively, this seems like the faster way to do it, and it's more ergonomic. So I like that approach. Math is complicated. Now you're learning about geometry to implement correct positioning object in a game world. Then I need to implement distance checking, pathfinding on a 3D map. So complicated. Writing a framework for emulating a World of Warcraft server. That's cool. I did a video on positioning the object in the game world. It was on the scene graph and the way projection matrices work. So recommend it. It's on my YouTube. You can do exclaim YouTube for it. The other thing I'd recommend is there's a really, really good, and I might have linked to it in that video. Let's see here. Today, rather than working more on it's this was the video. I just dropped it in chat. I guess I didn't put it in the comment. I did. Bob Nystrom wrote a book called Game Programming Patterns, which, whoops, oh, weird. I guess this link will work. It's some weird redirection link. Can I get this link? Here's a better link. Game Programming Patterns is this book that Bob Nystrom wrote that I just found super, super interesting and really helpful for doing something like that. So highly, highly recommend it. Okay, so what was my point here? My point here is, to your point, math is hard. So we're just going to go ahead and index things on rows for the moment, and then work out what's better. Do I want to implement from the other way? I don't know. Let's write a test. Why are my parens all screwed up in this test? It's distracting. Okay. Cool. Let's go test sparse matrix from D matrix. And we'll say let matrix I don't need this, I don't need this, I do need this, and fix our indentation. 1, 2, 3, 4 seems like a very reasonable matrix. This will just be from, and then let's assert sure, and let's say sparse dot. I don't think I can implement from going the other way, although that would be nice. Let's see here. Let's what's the best way to do this? I guess we can just say sparse 0 is 0 1.0 complex from 1.0. So, do I have to do .get? I don't remember. I thought I could index into these. Oh, it's because, duh. It's because I had to wrap this in a different type. So, call it get row. Let's see here. Get is fine, but then pub function get row, self row. I do not want to return a vector. I want to just return. Oh, hold on. This is absolutely not going to work. This needs to be a vector of usize. Let's get rid of this. I'm just gonna do this the way that makes sense to me, and then we'll optimize from there. So let's make this a hash map from usize to complex. Did I get the right number of angle brackets? I did. Let's call this a sparse matrix entry. Handlefa says, it's so surprising when I realized that if you're writing a server for something like World of Warcraft, you literally write a game without a GUI. You need to implement the whole logic of game on it. Yeah, that is a thing you absolutely need to do. Why is my source directory on gitignore? It's not. Where are you seeing that? Sparse matrix entry, sparse matrix entry. Let's update this to be sparse matrix entry. And let's actually implement this function. Self.data get I. This should return an option. Should it return an option? Actually, it doesn't need to. It can return a complex 0, because that's what it's going to mean if it's 0. So that should be fine. And then we might need to be able to get a row also. But we can do that later. And this ought to be not like this. This ought to be we get a row iter, we get a j iter, we say if coefficient isn't 0, then we need to check if sparse matrix contains key I, then yep, otherwise we insert the coefficient in J. Hashmap new. And we insert the row. That looks right to me. And this needs a specific type, which will be what? It will be a hash map. Hang on, this is not a very good name. This should be sparse matrix representation. Is a better name for that. There we go. That's a little better. Does Bevy have something for pathfinding? I'm not sure. I have not done pathfinding in Bevy. I suspect it doesn't. I haven't seen anything for it, but there might be. You should Google it because people have written crates on top of Bevy that might have something, but I don't think that it does. If I had to guess, I would say no, but I don't know. Okay. And now let's just fix this. Sparse matrix from to D matrix. From matrix algebra, dynamic, F32. It's not implemented for sparse matrix. That doesn't seem right. Kind of seems like I do that here. Matrix T, dynamic, vex storage, T, dynamic. Dynamic storage. Oh. Yeah, okay, that did it. Size, what's wrong with size? Didn't I implement size? Nope, I absolutely did not. Size self, return size. This can be get size and get 0, 0. It better be 1. And 0, 1. I assume this is right. I actually don't know what from vec does. Wow, this is 1 indexed. That's annoying. So 0, 1. So it seems like that's not how it works. It's filled column by column. Why is it filled column by column? That doesn't make a tremendous amount of sense to me, but okay. Whoa. Contents of the file is newer. I'm skeptical. Okay. Cool. That passes. And now can I implement from going the other way? Or can I not because because I don't own this type? I don't remember. assuming for a moment that this is right. Okay, I can implement this myself. That's nice. And to do it, I fill with zeros. And then I'm pretty sure. Let's see here. What is is there a set? Set column, set row. So I should just be able to set row here, I think. I think there's also a function. Actually, that's probably better. I'm pretty sure there's a dmatrix from function. Dmatrix from function. Yeah, there we go. This ought to be pretty efficient. Sparse matrix dot size. Sparse matrix dot size. And then the function can be we're just gonna get to return this at the end of the day. And then the function is like ij. The function is a function from usize, yeah. Sure. And this goes away. Okay. So in our test, we should be able to test that let original be dmatrix from sparse, and we want the original to be equal to matrix. The issue there is that we need this to be almost equal to, not equal to, so let's say original minus matrix dot norm is less than 001. Norm returns some horrible thing. It's annoying. How did I do this before? I've done this before. Don't I have like an almost equal to or something? Almost equals. Yeah, I just take the norm. Do I have to import normed? Norm should already be imported. Original minus matrix. Oh. Assert. Okay. And let's check this out. pathfinding you think is like a shortest path in a graph, like Dijkstra algorithm. Dijkstra, I never know how to pronounce his name. But you also need to generate path graph from 3D map. And you don't have any clue how to generate a path graph from a 3D map. But as you remember, pathfinding in a graph is pretty complex to compute. Yeah. So it depends on... So I think that if you try to do it just like voxel by voxel, which would be the sort of naive way to do it, right? To get the path graph would just be like voxel by voxel. You have this, whatever 6-sided thing each voxel, and it has a edge that connects it to each voxel next to it. I think it'll be really, really, really inefficient because you'll be like, a lot more about the structure than that graph will tell you. So I think you probably want to take that into account. Like, anytime you have a wide open area, you're going to be able to just take a straight line distance and count that as one edge. But I'd have to work out how to do that, and I don't know off the top of my head, that's for sure. Okay, did this test pass? No, it did not. Why? Because my code didn't compile. What happened? Ooh. I've seen these before, but usually when I cargo clean, they go away. I assumed it was a nightly thing. Curious. Okay, so assuming that this test passes and there's not something weird going on with my repo, then the next thing will be swapping in the sparse matrix in here, and then implementing the multiplication myself. What is happening? Oh, okay. It's just the value that got moved. Cool. That's fine. Just clone it. It's in a test. Not a big deal. One thing Handlefar about having to implement a game without the GUI, implementing all the game logic, like, that's kind of what you want to be doing anyway, right? There's this idea of model view controller. Like, you want to be separating the UI and the view out from all the game logic. The GUI is like a pretty separate concern from the game logic. Okay, cool. That test passed, which is great. So let's start swapping stuff out. Or I guess we can do our matrix multiplication on the sparse matrix, now that I'm thinking about it. So, let's do that. Function test sparse matrix. I want to test sparse matrix multiplication. Okay, and so let's do left-hand side is sparse matrix from sure, we can use 1, 2, 3, 4, 5 again. And then let's let RHS be sparse matrix identity. And then I kind of feel like I don't know, I guess this is fine. Assert that things didn't change. Oh, I should probably make my sparse matrix clone. And I'll make it debug also. And just a convenience function for identity, which takes nothing and returns itself. It takes a usize. I don't feel the need to cool. And then we're gonna need multiplication. And let's go ahead and put a few actual multiplications in here. Let's do like 5, 7, 6, 8. And I mean, this is obviously not an actual sparse matrix, but that's fine. And I'm going to assume that GitHub is doing the matrix multiplication right, although it may very well not be. That's easy to check. Okay, and then we want to impl mul for sparse matrix. Can I do this? I'm not sure I can do this. I think I might need to be explicit. GitHub, this is when I would like you to fill in my boilerplate. Otherwise, I have to remember it. Type output sparse matrix. Hey, there we go. Okay. So, it thinks it's doing the multiplication. Do I believe it? So I go through each of the rows. I go through each of the columns. if the right-hand side has an element with the left-hand side's column. So if the row of the right-hand side, this is backwards, right? This seems backwards to me. So we're looking at the ijth element. In which case we don't want to look at the jth row of the right-hand side. Do we? IJ. It's the ith row and the jth column. Is the point just... I should probably just write this myself instead of trying to work out Copilot's algorithm for it. Result. So this is the kth column. So we're inserting the to the ik element. We're updating it with the coefficient plus the right-hand side coefficient. Let's call this the left-hand side coefficient, just to be symmetric. And the left-hand side coefficient is the ij, so the ith row. And the right-hand side's coefficient, we're looking at the kth column and the jth row. So the same row as the column. This doesn't seem right to me. So let's do the example here. So, and this is kind of an annoying way. So this is 1, 2, 3, 4. So this is 1, 2, 3, 4 times 5, 6, 7, 8. And so we would expect this to compute by saying, okay, let's look at the first one and let's so it's 1, 3 times 5, 6. So 1, 3 times 5, 6 is 5 plus 18 is 23, which is what GitHub tells me, which is good. So here it's 0, 0, times 0, 0, 0, 0, 1 times 1, 0. That's what should get added. And do I believe that that's actually what's happening here? So 0, 0 is ij. And then we're looking at zero, zero K. Got it. Okay. This maybe should work. And this is just constructing it. Maybe should work. Little dicey. What's going on here? I can't subtract sparse matrices from one another. Sure. Let's just do results dot almost equals LHS and result almost equals this whole thing. And fix our parentheses. Which are not correct. Okay. And then we can just make almost equals a square matrix thing. Yeah, fair point. This is probably faster. This is probably faster. And we need a complex field. Okay. Almost equals LHS clone. Yeah, I guess this can just borrow. In which case I don't need to clone. And this can just be a reference. Okay. Let's see how we did. Failed. Okay, do I believe that this is the right order? So we expect this to be 23, and then 1, 2 times 6, 8 is 6 plus 16. It's 22. 3, 4 times 5, 7 is 15 plus 28 is 43 now. 3 times 7 is 20. 3 times 5 is 15. 4 times 7 is 28. So 33, 43. Am I doing this right? And then 3, 4 times 6, 8 is 18 plus 32 is 50. Am I crazy? So this is not even remotely close to right. This should be 22. This should be 43, and this should be 50. Skeptical of my ability to do mental math. Still fails. What's the result? Almost equals. This is annoying. Let's do D matrix from result. $19, $22, $43, $50. So did I just do the math on the first coordinate wrong? Because everything else looks good. 1, 2 times 5, 7 is 5 and 14. Yeah, that's 19. Okay. Okay, so our matrix multiplication works. And now we just need vector multiplication. Maybe we should benchmark these though. Just to see how fast this is. So if memory served, it took like 3 minutes to do it 10 by 10 previously. Test sparse matrix multiplication big. And what to do. What's the most efficient way for me to do this? I guess we can just use sparse matrix. Oops. LHS sparse matrix new 10. And then can I do, I wonder if I can do a square. Maybe that might be the easiest way. From D matrix, can I do square? From diagonal. There we go, from diagonal. Not that many though. But just 10. let's make it non-trivial. So let's say, let's just make this 0. Yeah, let's do that. And we'll just square it. Let result be LHS times LHS, assert, and we'll just assert that the result is 10 by 10. 1 through 10. Okay. Fine, we can clone one of them. Oh, but it's not 10 by 10. It was 2 to the 10 by 2 to the 10 that was troublesome. Okay, so that passes, which is good. But then let's say let size be 2u size dot power 10. And then this becomes size. And this becomes size. And now how do we do? Super fast. Super fast. Okay. Good stuff. Alright, that seems to be a victory. I hope. I mean, it makes sense. It makes sense that that's super fast. Okay, so now we can do. Let's commit this. Sparse matrix multiplication. Get push origin, and this is circuit refactor. Okay. This is exciting. Okay, so now we want to replace the matrix with a sparse matrix. And when we format, for now what I'm going to do is dmatrix from, again, I'm just trying to, I don't want to optimize anything, like I want to change the fewest things possible. Oh, interesting. I didn't remember implementing this. Okay. What we will do is self.matrix dot almost equals other. RHS. Expected reference, found reference. So what's the problem? Then we have a, I think I'm actually just going to do self.almost equals here because I'm pretty sure we have an almost equals function that I'm sure we're going to have to overwrite, but almost equals, yeah, we do. Oh, it would have needed to be, I understand what happened there. Okay, square matrix, new unchecked, so that's not what we want. We want, oh no, that is what we want. And then when we do multiplication, we do self.mate by, okay, so this we're still gonna have to implement. We haven't implemented that yet, but it will work at some point. These we are going to let's take these as sparse matrices. New unitary. Is more complicated. I think we're going to leave that as it is and say sparse matrix from sparse matrix. This, let's say, let D matrix be D matrix from matrix, and then all of these become D matrix. Again, not expecting this to be fast. I'm just trying to get the code to compile again with the two optimizations that I care about handled. So like from vec normalize, we can just say square matrix from identity, we just say sparse matrix. Oh, sorry, that should be sparse matrix. Sparse matrix from sparse matrix. Self.matrix gets size. Should probably just be size to be consistent. And what else we got here? Get coefficient should be self.matrix.get. Permutation we should probably implement directly. Almost equals should just be self.matrix.almost equals RHS.matrix. Let's see. So for this, we can say let data be hash map. Let me data be hash map new, and then we do data I is column is C. C is fine. And we say let C be hash map. Let's see here. Let's see hash map usize to complex. and then this becomes sparse matrix, new size data. All right. Data I. Okay. For get, we just say self.matrix.get I j. Wait, what happened? Okay, this is no longer needed, and we just get ij. Okay, we need to be able to multiply with a scalar. We need to be able to do tensor products. Tensor products are going to be a little weird. For now, let's do D matrix from this. D matrix from this. Sparse matrix from this. Again, just want to get something working before we try to optimize it or rewrite various functions in here. Same story here. D matrix from this and sparse matrix. Wonder if I want to say. I don't want to just implement from because I like having to specify the new unchecked. I think it's okay. Okay. Getting there. D matrix from and I don't think I ever actually used swap columns. I think I'm just gonna get rid of it. I think that was a relic from something else we were trying to do. Okay, so we have to be able to multiply by a scalar, and we have to be able to multiply by a vector. And then in our tests, we need sparse matrix from this. Sparse matrix from this. It's probably a nice way to do this with regexes or something, but I don't think I have so many of them that it's going to be terrible. Sparse matrix from out there kind of are a lot of these. Kind of are a lot of these. Wait, why am I doing swap columns? I think I decided this never actually gets used. Okay. Cool, and those are our sparse matrix tests. Do I not have determinant already defined? I guess I don't. Same thing here. Okay. All right, and so then we just need to implement the other multiplications. So impl mul complex F32 for sparse matrix. And all we do here is multiply everything out. Why do I have any K's at all? Oh, I don't. It's just I's and K's. Okay, these are just the keys. Cool. That looks good. And then mul, sure. And then mul of D vector. Yeah, and this one's the super efficient one, because the only time we have to do any calculation at all is when there's an element. Right, so we instantiate the vector. If there's an element, then the resulting row then the ith element of the vector gets appended. That looks correct. We should write a test, but it looks correct to me. Okay. Do you have the swap basis? Yeah, and again, we never use this. So let's get rid of the dead code. Yep. So what's the right way to do this? Dot insert IC. That works because it's mutable. Cool. And we got one more thing that's not compiling somewhere. Where are my red squiggles? Data needs to just insert an I. Couple more little things. Sure, we can clone this. We'll optimize later. We can clone this. Okay. Okay. So let's see how we did. Let's see how we did. Okay, 15 tests failed, so something didn't quite work right. What's the simplest test that failed? Permutation matrix. This should not totally surprise me because I messed with the implementation of it. Panicked at an assertion failing. This one. Quantum gate, permutation, square matrix, permutation. Like, obviously the issue is here. This needs to be J. The column. And also this should be called a row. And we can go ahead and just call it a row. And why can't we collect? Hey, all of our tests pass. Incredible. Okay. And our multiplication still happened fast. So, now, let's go back to, what, in square matrix, we have a test somewhere that tests matrix multiplication. I think. Yeah, so this one. So if we make this 10, this used to be really slow. It is now very fast. Excellent. Same thing in here. Let's make it n qubits, 10 qubits. It's so speedy. Okay. Incredible. What happens if we do our visualization now and we do it with like a bunch of qubits? Like 5. Is it like way faster now? Cargo run. I mean, at some point the drawing is also going to be a bottleneck, but okay. Wouldn't call this way faster, but I mean, that's because this isn't, yeah, the drawing is becoming the bottleneck, so that's fine. Let's leave this on 4. Let's get at all. Update internals of square matrix to use sparse matrix. cubes. Okay. And so now in our quantum algorithm, how's this test doing? Because this was the test that sent us down this path of, okay, so it failed to allocate a huge number of bytes. That's going to be an interesting separate problem to need to solve. But it tried to, which is good. It didn't used to try to. It used to just be slow. So this is very good. This is very good. Okay. So let's try to work out what's happening here. So stack buffer overflow. So where do I think that we might be buffer overflowing? Where is it bombing out on instantiating? Yes. Okay. So it's during the instantiation. The number of qubits is 8. Okay, so it's bombing out during. So what happens, just for the moment, if we make this the simplest possible non-trivial case, which is 6. It dies. Wait, it dies because it was in debugger and the linker got confused. Okay, so now it's trying to run. Still getting bottlenecked somewhere. Still probably need to heap allocate somewhere. Test failed, which we expect. And it failed for actual reasons. Okay. So what's going on here? Self.circuit. Target control. We tensor product. n qubits. N qubits is 2 times this. Wait, no. Divided by 2. Is what it should be. And it's getting to the run step. And the run step is going to involve a bunch of matrix multiplication, but that should be fast now. Clearly there's still some instantiation slowness, but, and our algorithm failed, but that's fine. We haven't implemented the algorithm yet, so. All fix bug in counting qubits. Nice, nice, nice. Okay, so the plan from here is going to be obviously to implement the rest of the algorithm. It seems like we're going to have to work out where we're overflowing the stack when n is 15. And then find a way to heap allocate that. Because I don't think this is a case of the call stack being overrun. I think this is literally the stack is being overrun. We can also just increase the size of the stack, which honestly is what we might do. But next up is going to be the actual algorithm. In particular, right now, we just stub out the periodic function, which is the key to the whole thing. We need to produce it instead. So I think I'm going to stop here. Been going for an hour and 45 minutes or so. Stopping a little early. But hopefully it has been interesting. I'm pretty happy with how the refactor went and how our home rolled sparse matrix multiplication algorithm worked. I also think it was a nice example of GitHub Copilot being super helpful because I did not really have to write that algorithm. I had to check it. I had to make sure that it worked. I had to write tests for it. But at the end of the day, once I set up the data structure correctly, then GitHub Copilot was able to write it itself, which is super cool. These sorts of low-level things are, exactly the sorts of things that get written over and over again and don't really need to be. And I understand in theory what it needs to do, but actually writing it is a pain because I have to keep track of I's and J's and K's. And GitHub already knows how to do that. So pretty pleased with that. And I'll leave it here. Hope everybody has a good day. I should be back tomorrow. See you later.